Alright, so today's video I'm going to build a visible light spectrometer. Now there are a bunch of videos already about building very simple ones with a webcam. However, I want to build this a little bit differently. So first of all, what's a spectrometer? In terms of light, a spectrometer takes light, splits it into its component wavelength and measures how much or how intense each wavelength of light is. And this is very useful because elements like neon or metals and also organic compounds either emit or absorb light at a very specific wavelength. And with a spectrometer you can analyze pretty much anything. Alright, so the simple version works like this. You take a cheap camera or just a camera in general and you place it in a box, and the box has a very tiny slit. Okay, this is not completely in the middle, but whatever. It's basically in a box, in a light tight box, and what you do is you place a diffraction grating at an angle in front of the lens of the camera, and the light that enters into the slit gets split by the diffraction grating, and the diffraction grating is basically projecting the spectrum onto the camera, and then you use a program to read out the image the camera produced. I definitely could build this in a day, but as my subscribers know, I definitely take longer to make these videos. Okay, mostly because I'm lazy, but I'm going to build this differently. So I'm going to take away the camera. So what I'm going to do is I'm going to have this in a box again. So you can draw the same box. And I'm also going to have a very, very tiny slit. Should be here, I think. Very, very tiny slit in the middle where the light can enter. And instead of using the camera, I'm going to use a single sensor. And I'm going to have a slit here. And what I'm going to do is I'm going to mount the diffraction grating on a rotating post. And I'm going to have the diffraction grating like this and can rotate it. And as you rotate it, you're projecting the other parts of the spectrum. So if you have like red here and violet here or blue here, you can basically change what's hitting this slit and change what wavelength the single detector here sees. So this is different to the camera because the camera basically sees the entire spectrum. The camera sensor can record basically the entire spectrum at once, and I'm going to replace it with a single sensor and rotate this. This method is not necessarily better. The cameras are actually pretty good and they're reasonably good sensors for this, but I just want to try out to have a single sensor and have the signal actually be read out by my oscilloscope. So with a camera you need to connect it to USB or take a picture, and you have to read it out in a program and program this stuff. And I just want to use my oscilloscope to make these spectra. One problem with this is that you need to rotate the diffraction grating. With a camera it would be stationary, but you need to rotate it. And you also need to track the position of the diffraction grating. This obviously adds some more difficulty to this, but I just want to build it this way. So let's see how well this works. What I don't really understand about these super simple webcam spectrometers is that pretty much always the camera and the diffraction grating are placed some distance away from the slit. But in my opinion, this should make the resolution worse because from the slit, the light basically like fans out. I'm pretty sure it has a name, but like the light spreads out. And as far as I know, this is not very good. I'm not really sure about it, but it should cause some overlapping because the angle is very important. The angle of the diffraction grating and the light. And as far as my research goes, normal spectrometers have the slit, and then they actually have a lens, and this lens basically stops this spreading out and makes the light rays completely parallel or completely in line. And this is called a collimator lens, and as far as I know, these are pretty much necessary. So I'm not sure if this causes problems. Apparently it doesn't, but maybe it does reduce the resolution. I'm really not sure about this. I'm not really knowledgeable about like optics and stuff. But in my opinion, it should reduce the resolution. But I could also be totally wrong, and this doesn't really have that big of an effect, or the collimator lens is not that important. I don't know, maybe I can find it out in this video, but I think I will try to build it with the collimator lens. So I talked about using a single sensor instead of the camera, and I want to make it as sensitive as possible. So I want to use photomultipliers, and I have here a photomultiplier tube, and I have here some silicon photomultipliers. And I'm not going to use the photomultiplier tube because it only is sensitive to 300 to 650 nanometers, which is slightly less than the visible range. The visible range actually goes to 800 nanometers, so you have a little bit of the red spectrum not covered with this. These are actually super broadband, and they're actually sensitive not into the infrared, but actually into the UV. So potentially you could also do UV spectroscopy a little bit. But yeah, this is a little bit narrow in spectral response, and these are pretty great. So they're also super compact. So I'm going to use these silicon photomultipliers. I also wanted to play with these for quite a while now. One drawback of these silicon photomultipliers is that they are not super commonly available. I had to get them from a special electronics supplier. But other than that, yeah, you need to be careful. They are super tiny and SMD components. So I need a circuit board to mount these on to handle these somehow. And that's why I reached out to my sponsor JLCPCB again. They're literally making this project possible by providing such a tiny PCB for the silicon photomultiplier, as well as a circuit board for the power supply and the amplifier for it. They also provide CNC machining and 3D printing. So click the link in the description to make your projects professional and precise with JLCPCB. So let's talk about the electronics. I put everything together already. It looks a bit messy. I had to add some components, but I will get into that in a moment. I wasn't sure how to drive and amplify these silicon photomultipliers, so I looked at the internet and found a few designs and basically picked from these designs to make a circuit that works. So here you can see the circuit diagram already. The way this works is the silicon photomultiplier is down here, and it needs to be supplied with a stable, relatively high voltage. And the way this works is I have 55 volts here, and I have a voltage regulator, and this regulates it down to, I think, 48 volts. It depends on what silicon photomultiplier you have. But this regulates it down. There are some feedback resistors, a capacitor. So this is just this area right here is just the voltage regulator. Then here I have a resistor. This is a so-called quench resistor, and this basically limits the current to the silicon photomultiplier. And I have another capacitor here, and here is a connection to the silicon photomultiplier. From there it goes over a 1K resistor to ground, and when light hits the silicon photomultiplier, a voltage is generated across this resistor, and this is amplified by this amplifier right here. The amplifier on this circuit is actually wrong. It's actually the OPA354, and this is a very high speed amplifier to amplify these pretty high speed pulses. But else it's a standard op amp. It's set up with a gain of 10. It has its own 5-volt supply. And I put a capacitor here just in case I want to smooth out this voltage that's coming out of this. But it turned out I need much more smoothing on the output. So originally I just put a connection for a BNC port right here on the output. But I realized that for the spectrometer, I need a pretty smooth output depending on how much light hits the sensor. However, from the silicon photomultiplier, you get a bunch of pulses. So I needed to fix that. So this is probably a bit silly, but to fix this, I just soldered a low pass filter with a cutoff frequency of only 400 Hertz onto the output. So this is right now a coil with 1.6 millihenry, I believe, and a capacitor with 46 microfarads. And by doing that, I'm getting a really smooth signal out of there instead of these pulses. Not sure if that's a very good solution, but it works. Alright, let's put all of this together. In the beginning I sort of mentioned how all of this works, and I already worked on this a little bit. I'm going to use this plastic box. I also have a lid on there, and I have made some slits. These are razor blades, and I just screwed them onto a piece of wood, and the light can shine through these slits. And I made one for the detector, and right here is one for the input where the light is going to shine in. And if I turn this a little bit, you can see I made a hole right here. Here is the light that's coming in, and it's going through this slit. This is the same thing as this thing right here. And here I have a collimator lens, and I actually found out why these are useful. Because the light beam that's coming out of this slit is dependent on what angle the light is shining in. And if your light is not exactly at the same location every time, you're going to mess up all of your measurement. And the collimator lens takes this and it makes the light shine out at a very specific angle every time. To be honest, I should have realized this at the beginning, because this is literally what a collimator lens does. It takes light from different angles and makes it into one beam. That's why they're used in lasers. Next, the light is going through this diffraction grating, and right now it's just on a piece of cardboard, but I'm going to put this on a rotating post, because the light is going to split into a spectrum that's going to be projected right here. And if I rotate the diffraction grating, I'm going to have different parts of the spectrum on this slit. And behind this slit is going to be the detector. And for example, if I have it rotated like this, I have the blue part of the spectrum hitting the detector. And if I rotate it like this, I have the red part of the spectrum hitting the detector. And this way I can scan through the entire spectrum by rotating the diffraction grating. And that is basically it. Obviously, I'm going to put a lid on there so it's all protected from light. But yeah, I'm very curious how well this will work because everyone is doing it in a different way. And it's the first time I'm building such an optical system thingy. All right, I've put together everything. I put the diffraction grating on this rotating screw so I can rotate it and scan through the spectrum basically. And yeah, I'm happy to announce that it works. I'm not that happy with the resolution, but before I build another version, I want to show on camera how well it does work so far. So here at the input, I have a fluorescent lamp, and this will create an easily recognizable spectrum to analyze. And I'm going to display the spectrum or also measure the spectrum on the oscilloscope that's off screen here. And then we can see and analyze the spectrum there. All right, I've put the scope on a very large time scale, so it's very slow. And I'm just going to turn the diffraction grating very slowly. And you can see some peaks appearing as I turn the diffraction grating. So here I went forwards or in one direction, and here I went backwards. And I think the peaks here, these big, small or narrow peaks, are from just the light ray. That's not part of the spectrum, but from here to here, that's the spectrum, I believe, or like from here to here. So you can see it's repeatable, but I mean, it depends on how you collect the data as well. But the spectrum is very rough, so you can just see like it's going up here, a bit down, and up here again. And I believe the spectrum of the fluorescent lamp has like 2 large peaks, but it also has a bunch of large peaks in between, and we can't really see that even when I try to make a very a nicer spectrum. And another problem is as you zoom in, you can see all this noise, and this is actually from the 60 hertz that's coming from the wall power. So because the lamp is driven by 60 hertz from the wall power, it's going to flicker at 60 hertz, and you can see this in the spectrum. So yeah, that's a bit of a problem. So how am I going to increase the resolution of this spectrometer? Right now, the distance from the slit to the detector is not that big. I could probably push it a little bit this way, but the electronics is also taking up some space. But what I decided instead is get a bigger box. This one is only a little bit bigger, but it's a bit more wide. Because what I'm going to do is I'm going to build it exactly like this. But I'm going to put a mirror here. So the spectrum can basically travel here, get reflected here, and travel back. So it's basically twice the distance to travel, and it has more distance to spread out. And this will increase the resolution of the spectrometer. All right, this is the final version now. Like I said, I have installed a mirror, so the light goes in here, bounces off the mirror, and then into the detector to increase the light path. This mirror is actually a first surface mirror, which means that the reflective surface is at the front of the glass and not behind the glass. And this is supposed to improve things somehow, maybe that the light is not going to travel through the glass and interfere somehow or whatever. But this mirror did cost 50 euros, so I'm glad the video is sponsored. What I also did is I increased the amplification of the op-amp by replacing this 1K resistor with a 10K resistor. And now the amplification is not times 10, but times 100. So this made it a little bit more sensitive, and it helped a little bit. What I've not mentioned yet is that we have to track the position of the diffraction grating because the spectrum will depend on the position of the grating. So I installed this rotary encoder, and this will interface with a magnet that's glued onto the diffraction grating, and this will track the position and give out an analog signal for the second channel of the oscilloscope. So right now the system does work pretty okay. It's not super sensitive like I wanted it to be in the beginning. Also, it needs a lot of fiddling and adjusting. The slit size needs to be adjusted, and the position of like the detector and the slit here and the collimator lens. So it's very fiddly, and also very fiddly to get a spectrum. So that's a bit of a downside, but it does work fairly well. So let's record some spectra. I have here an LED. I used the fluorescent lamp before, but because the AC is messing up the signal, I switched to the LED. And I actually have a data sheet for the LED, so I can also know exactly what the spectrum is that's coming from this LED. So I will use that. All right, I have my LED down here, and it's shining into my spectrometer, and up here I have the oscilloscope recording all of this. And when I turn this, you can see I can record a spectrum. Right now I don't have the light that's coming from the window blocked, but if I do that as well, the spectrum will be much cleaner and stuff. So let's do this, and then I will show you the spectrum I can record from that. So this is the spectrum I recorded. The blue trace right here, that's the encoder, and with the encoder we could calibrate this and would know for sure that this peak is a certain wavelength. I didn't do this right now, but we could like calibrate this and see, okay, here is blue, a certain wavelength of blue, and here is red. And that's how we would calibrate all of this. I will put the spectrum from the data sheet down here, and you can see, yeah, it's kind of similar. You can see here, this is the blue peak right there, and then it goes up, and this main peak is the red, more on the red spectrum, and then it falls off relatively slowly. It doesn't really have the small green hump there, so it can't resolve that, but it looks reasonably similar, so I'm pretty happy with that, considering that I just put this thing together myself. So yeah, looks pretty good, I think. Unfortunately, I could not get a spectrum of neon. I tried some neon lights and stuff, but they were just too weak, and the spectrometer is not so sensitive. So unfortunately, I couldn't record any spectrum of that. But I tried sodium. I was just burning sodium, table salt in my burner, and I just got enough light to record a spectrum. And it also looks very similar to the spectrum of a sodium vapor lamp. So I'm also really happy that that works. All right, so I think if I want to improve this any further, I would have to do another redesign. Because instead of the silicon photomultiplier and using this crappy filter idea, I probably should have used the photomultiplier vacuum tube instead, because it gives out more of a DC signal and not these pulses from the single avalanche photodiodes. So I think the next version needs a photomultiplier tube. Or I would have to do some digital processing and count the pulses or whatever. I don't know. I'm not really keen on that. I don't really like that. I kind of like analog stuff. So I think I'm going to use the vacuum tube for that, for the next version. However, I'm not going to build another version in this video because I want to make some progress on the other projects, most notably the vacuum tubes, also the Oswald process. So if you want to see any of these videos, then subscribe, and until next time, bye.